sir? Hello.
Doctor, is it your slides are visible, but you are on very first slide, is it? Yes, your cursor is moving. Yes, fine.
Yeah. Okay. The title of my presentation: a hybrid mathematical framework integrating chemical graph theory, machine learning, and multi-criteria decision making for predictive molecular property modeling. These are the contents of my presentation. Is it audible, sir? Hello.
Yes, doctor, you are audible.
Okay.
Audible. Yes, you are audible. Please continue.
Okay, sir. Thank you. So these are the contents of my presentation: introduction to graph theory, basics of graph theory, molecules, structure and topology, chemical graph theory, topological indices, QSAR and QSPR, graph-based descriptors in machine learning, statistical parameters in evaluation, multi-criteria decision making. Coming to first slide, introduction to graph theory or introduction of graph theory. Graph theory began with Leonard Euler in 1736, who worked on the famous 7 bridges of Königsberg problem. It has since evolved into a major branch of mathematics used in computer science, chemistry, and network analysis. Growth and development of graph theory. In the 19th century, used in electrical circuits and algebraic structures. In the 20th century, formalized in discrete mathematics, operation research, chemistry, and applied to computer science. In the modern era, used in power algorithms, artificial intelligence, social network analysis, and chem informatics. So now move on to basics of graph theory. Graph theory is a branch of mathematics that studies graphs, abstract structures made up of vertices and edges. It is used to model relationships and interactions in systems such as molecules, computer networks, and social structures. Key concepts of graph theory. A graph G is defined as G is equal to V comma E, V be a vertex set, E be a edge set. Set of vertices, examples are atoms, sites, and people. Set of edges are examples chemical bonds, roads, and friendship. Here we consider one simple graph. So be an example of simple graph, and this graph having 3 vertices and 3 edges. Here vertices are called A, B, and C. Edges of the graph is A to B, B to C, and A to C. So we have 3 vertices and 3 edges forming an triangle. Then we move on to types of graphs. Here simple graph, no loops or multiple edges in the graph called as simple graph. Example, triangle. Then multiple graph, multiple edges between same vertices. Example, road between A and B. Then graph with loop, edge connects a vertex to itself, is called graph with loop. Example, atom bonded to itself. Then directed graph, edges have direction, then it is called as directed graph. So here example, one-way street. Then weighted graph, edges carry weights, is called as weighted graph. Here example, for example, A to B 5 km, B to C 2 km. Here 5 km and 2 km represents the weights of the graph, called as cost and distance. So then we move on to complete graph. Every vertex connected to every other vertex called as complete graph. Here K4 is equal to fully connected 4-node graph. Then bipartite graph. Vertices split into two sets, edges only between sets. Example, students or courses, student courses. Then tree, connected graph with no cycle is called as tree graph. Examples are family, tree or molecule with no rings. So here these are the examples of or pictorial representation of above graph. First one be a simple graph, second one be a multi-graph, third one be a graph with loop, fourth one be a directed graph, fifth one weighted graph, sixth one complete graph, seventh one bipartite graph, eighth one be a example of tree. So these are the some types of graphs. Now we move on to definition of molecules, structure and topology in chemistry. First, we discuss what is a molecule. A molecule is a group of atoms chemically bonded together. It represents the smallest unit of a compound that retains its chemical properties. Then topology describes how atoms are connected and captures molecular shape, branching and rings. Example, here we consider molecular structure of methane. Already we know that molecular structure of methane and formula is CH4. It means that one carbon atom and 4 hydrogen atom. So here 4 hydrogen atom connected with one carbon atom. So it's called as molecular structure of methane. So why structure matters? Determines boiling or melting points, solubility, bioactivity, toxicity. And chemists use structure to predict behavior before synthesis. Then predicting chemical behavior. Physical properties. Already we are knowing that physical properties of the chemical compound commonly are boiling point, melting point, density, refractive index, all can be estimated from the structure of the molecule. Then reactivity. Structure reveals reactive sites and stability. Solubility. Polarity and size predict dissolution and bioavailability. Then stability and decomposition determines whether a compound is thermodynamically or kinetically stable. So these are all represent the predicting chemical behavior of the molecular structure or chemical compound. Then we move on to chemical graph theory. So chemical graph theory is the branch of the mathematical chemistry that represents molecular structures as a graphs and applies graph theoretic methods to analyze and predict their properties. So here we consider one chemical structure called as ethanol. Molecular formula of ethanol is C2H5OH. So here atoms are represented as vertices, bonds between atoms are represented as edges. So graph theory helps to analyze molecular structure and properties. So here this is represent the molecular structure of ethanol. So ethanol containing 2 carbon atoms, 1 oxygen atom and 5 hydrogen atom. Connecting these we get the molecular structure of ethanol. Then we move on to important definition in the chemical graph theory called as topological index. So a topological index is a graph invariant that compresses the structural features of a molecular graph into a single numerical value used for correlating or predicting chemical properties. Topological indices are usually derived from hydrogen suppressed molecular graphs, where atoms are represented as vertices, bonds are represented as edges. These are widely used in QSAR or QSPR modeling to correlate chemical structure with biological or physicochemical properties. Here, QSAR called as quantitative structure activity relationship and QSPR called as quantitative structure property relationship. Then we move on to types of topological indices. Here in this discussion, we discuss only two types of topological indices. These are called as distance based and degree based. So distance based topological indices means that use shortest path distance between two vertices. Example of distance based topological indices, first one is Wiener index. So here Wiener index represents the sum of all shortest path distances. Then degree based indices use the degree of each vertex called as degree based indices. Example of degree based indices, Zagreb indices based on squares or product of vertex degrees. Then distance based topological indices. The Wiener index was proposed by American chemist Wiener in 1947, and he demonstrated that it correlates with boiling points of alkanes, making it one of the earliest and most influential distance-based topological indices in chemical graph theory. So, Wiener index is mathematically defined by W is equal to summation of Dij over the summation I less than j, where Dij is the shortest path between atoms I and j in the given molecular graph. Here we consider one structure be example of hydrogen suppressed butane. So molecular formula of butane is C4H10 as a straight chain of 4 carbon atoms. So here in the figure shows C1, C2, C3, C4. These are connected with C1 connected with C2, C2 connected with C3, C3 connected with C4. So now we using the given hydrogen suppressed butane structure, we need to find the Wiener index. So here first distance between, first we identify the distance between carbon atoms. So first distance of C1 to C2, 1, distance of C1 to C3, C1 to C3, 2, distance of C1 to C4, 1, 2, 3. So 3. Then distance of C2 to C3, 1, and distance of C2 to C4 is equal to 2. Then distance of C3 to C4, 1. So now we using this in the definition of Wiener index, W is equal to summation of Dij over the summation I less than j. Then we have 1 plus 2 plus 3 plus 1 plus 2 plus 1 is equal to Wiener value is equal to 10. So with the example of distance based topological index. Then we move on to degree based topological indices. So first, the first and second Zagreb index were proposed by Ivan Gutman in 1970s. These are the earliest degree based topological indices in chemical graph theory, used to describe molecular branching and connectivity. These indices are based on the degree of each vertex and in the molecular graph. The degree of a vertex is the number of edges connected to it. So here these are the definition of first and second Zagreb indices. So first Zagreb index is denoting by M1. M1 is equal to summation of degree of U plus degree of V over the summation UV belongs to a set E. And definition of second Zagreb index M2 is equal to degree of U into degree of V over the summation UV belongs to E. So these indices help quantify molecular branching and are useful in QSAR or QSPR studies. So now we consider one chemical structure to find the value of first and second Zagreb indices. So here chemical structure is called as propane. So molecular formula of propane is C3H8. It means that 3 carbon atoms, 8 hydrogen atoms has a branched carbon skeleton. So here we consider hydrogen suppressed molecular graph of propane. So this figure shows the molecular graph of propane. So here C1 connected to C2, C2 connected to C3 and central carbon C2. Vertex degree of C2 is equal to 2. It means that two edges are connecting between C2. So it means that degree of the vertex is equal to 2. Then terminal carbon C1 and C3. So here vertex degree of C1, here only one edge connected to C1. It means that degree of the vertex C1 is equal to 1. And C3, the vertex degree of C3 is equal to 1. So now edges are or edge partition of hydrogen suppressed propane. Here we have 1, 2 types of edges is equal to 2. Then by the definition of first Zagreb index, M1 is equal to 2 times of degree of U plus degree of V. It means that 1 plus degree of U is equal to 1 and degree of V is equal to 2. Then we have 2 with 3 is equal to 6. So M1 of graph G is equal to 6. Then second Zagreb index. By the definition of second Zagreb index, definition of second Zagreb index is summation of degree of U into degree of V over the summation UV belongs to E. So from the molecular graph of propane, we have two edges of the types 1, 2. So by the definition of second Zagreb index, here 2 times of degree of U into degree of V, degree of U is equal to 1 and degree of V is equal to 2. So implies M2 is equal to 4. Then another one most popular index is called as Randić index. Randić index is defined by summation of 1 over square root of degree of U into degree of V over the summation UV belongs to E of G. So here we consider one molecular graph of chemical structure called as isobutane. Molecular formula is C4H10. So here be the molecular graph of isobutane. So molecular graph of isobutane, C1 connected to C2, C3 and C4 and this molecular graph forming 3 edges of the types C1 degree, 3 edges are connected to C1. It means that degree of C1 is equal to 3 and C2, C1 connected to C2 and connected only one edges. So degree of C2 is equal to 1 and then degree of C3 is equal to 1 and degree of C4 is equal to 1. Then we have 3 edges degree 1, 3. So edges are 1, 3 is equal to 3. So now by the definition of Randić index, here summation of 1 upon square root of degree of U into degree of V. So we have 3 edges. So 3 into 1 upon square root of degree of U is equal to 3 and degree of V is equal to 1. And then on simplification, Randić index value is equal to square root of 3. So now let us move on to QSAR and QSPR. Already we discussed QSAR means quantitative structure activity relationship. QSPR means quantitative structure property relationship. So usually QSAR uses molecular descriptors to predict biological activity of compounds, and models relate to structural features to biological response such as toxicity or enzyme inhibition. Then can be regression or classification. QSPR, it is similar to QSAR but predicts physicochemical properties instead of biological activity. Examples include physicochemical properties includes solubility, boiling point, reactivity, and biodegradability. So next we move on to machine learning for molecular prediction. Why we need machine learning in chemical graph theory? So machine learning techniques in chemical graph theory enable the extraction and integration of complex molecular descriptors through data-driven modeling. These models objectively learn patterns that relate structural features to biological activity. Now, when applied to 20 anti-cancer molecules, machine learning algorithms generate predictive scores or classifications for each compound. Consequently, they provide a scientifically robust basis for identifying the molecule with the highest predicted anti-cancer potential. So, next we move on to machine learning workflow using topological indices. So, these are the steps involved in machine learning. So, first one is molecular representation, second one is descriptor extraction, third one is statistical parameter formation, fourth one is machine learning modeling, fifth one is model evaluation. So first one is molecular representation. First, we represent the molecules as a graphs, atoms as nodes, bonds as edges. Then descriptor extraction. So based on the vertices and edge partitions and definition of topological index, first we compute the topological indices like Wiener, Randić and Zagreb indices. Then statistical parameter formation. So build future vectors. We consider x is equal to first index, second topological index, third topological index, and so on. And compute statistical summaries. Statistical summaries includes mean, variance, skewness, kurtosis, and correlations. Then we build a model. So machine learning modeling. First, we train machine learning models by using random forest, support vector machine, GNN, XG boost to map X tends to predicted property. Example, boiling point or toxicity. Then model evaluation. So based on the statistical parameter, we assess the performance using metrics like R correlation coefficient between index and considered physical properties. Then root mean square error called as RMSE. Then mean absolute error called as MAE. Then coefficient of determination R square. Then Pfizer statistic or F statistic, then significant probability P value, and cross validation, etc. These metrics ensure the accuracy and reliability of QSAR or QSPR models and predict the properties of new molecules. Next, we move on to MCDM techniques for molecule selection. So MCDM techniques helps to rank and select the best molecules using their topological indices. So MCDM techniques in chemical graph theory allow multiple topological indices that describe different structural and physicochemical aspects of molecules. This ensures that drug molecules are assessed objectively across all relevant structural criteria. When applied to 20 anti-cancer candidates, MCDM methods compute a comprehensive performance score for each molecule. As a result, they enable a clear and scientifically justified identification of the highest ranked molecule among all alternatives. So, commonly used MCDM methods are Topsys, Wiener, and AHP. So, Topsys means technique for order preference by similarity to ideal solutions. Usually, Topsys methods are represent rank molecules based on their closeness to the ideal solution. Then Wiener. Wiener means Welse Kritizomuska optimizacija I compromisin regency. Focuses on finding a compromise solution among multiple criteria. Then AHP, analytic hierarchy process, uses pairwise comparisons to assign weights to the criteria and rank alternatives. Now we move on to first MCDM method called as Topsys. So steps involved in the Topsys method includes first one is normalize the decision matrix. Normalize the decision matrix. Here Rij is equal to Xij upon square root of summation of Xij whole square over the summation I varies from 1 to m. So here Xij original value of the alternative I for criterion j. Rij normalized value, m number of alternatives. So then second step, compute weighted normalized matrix. So here Wij is equal to Wj into Rij. So Wj called as weight of criterion j and Wij called as weighted normalized value. Then third step, determine ideal and negative ideal solution. So Vj plus maximum value of Wij. Vj plus is equal to minimum value of Wij. Here maximum of Wij represent the beneficial criteria and minimum of Wij called as the cost criteria. Then Vj minus minimum of Wij, Vj minus is equal to maximum of Wij. Then calculate Euclidean distances. Formula to calculate the Euclidean distances di plus and di minus. So here di plus is equal to square root of summation of Vij minus of Vj plus whole square over the summation j varies from 1 to n, and di minus square root of summation of Vij minus Vj minus whole square over the summation j is equal to 1 to n. So finally we compute relative closeness. Formula to compute the relative closeness is Ci is equal to di minus upon di plus plus di minus. So here based on the above steps, we consider one molecular structure called as molecular structures called as propane, isobutane, and butane. Based on the vertex and edge partitions, here we compute the topological indices. Computed topological indices are called as M1, M2, and F. So F is called as forgotten topological index. So we consider these are called as beneficial criteria. So now based on the values of these topological indices, here we write the decision matrix. So decision matrix is denoting by D is equal to Here first column values represents the first Zagreb index values of propane, and second column values are represents the second Zagreb index values of butane and isobutane, and third column values are represents the topological index values of butane. So forgotten topological index values of butane. Here each row alternative molecule, each column criterion M1, M2, F, higher values are assumed to be better. So then we normalize the decision matrix. So we normalize the decision matrix in the Topsys method. First, we use the formula Rij is equal to Xij upon square root of Xij whole square, summation of Xij whole square. So now norm of M1. Norm of M1, it means that square root of values of sum of square of values of M1. It means that square root of 6 whole square plus 12 whole square plus 10 whole square. Then norm of M1 is equal to 16.733. In the similar manner, norm of M2 is equal to square root of squares of sum of second column values. It means that M2 values. So norm of M2 is equal to 12.688. Then norm of F, forgotten topological index. So definition of forgotten topological index is f of g is equal to degree of u whole square plus degree of v whole square. Based on the edge partitions, vertex and edge partitions of propane, isobutane and butane structures, we get the forgotten topological index values are 10, 30, 18. Then using these values, norm of F is equal to 36.385. Then we move on to next step, normalized matrix. Normalized matrix, here normalized matrix is equal to Rij into Wj. Rij into Wj, it means that here Rij 0.358 into 1 by 3. So R value of R is equal to normalized matrix 0.358, 0.315, 0.275. In the similar manner, second and third row values. Then apply equal weights. Here we consider the equal weight criteria. So here we consider three indices M1, M2 and F. We assign the equal weights. Then M1 takes 1 upon 3, M2 takes 1 upon 3, F takes 1 upon 3. So equal weightage criteria. So W is equal to. Then weighted normalized matrix.
Sir, we are facing difficulty. Sir, we are facing difficulty for listening you. Can you please turn off your camera so that data should be transferred smoothly? So your voice is cutting in between them.
Okay, right, sir.
Okay, wait a minute, Doctor, wait a
Now
minute.
is it
Thank you
audible,
very
sir?
much. Yes, you are absolutely right, audible. No issues from your side. Any participant, if he or she have any kind of issue or question, please write us. Don't interrupt during the talk, please. You can message us, you can use WhatsApp or in the comment box. Thank you very much. Professor, please continue. You are going very good. I am understanding all the steps very interestingly.
Thank you, sir. Thank you very much.
So please continue.
Okay. Sir, okay. So here, first in the Topsys method, normalize the decision matrix. Here decision matrix values are obtained from the topological indices, indices, first Zagreb index, second Zagreb index, and forgotten topological index. So for the structures, propane, isobutane, and butane. So then normalize the decision matrix. So here formula to compute normalize the decision matrix Rij is equal to Xij upon square root of Xij whole square over the summation I varies from 1 to n. So we normalize the matrix. First we find the norm of M1. Norm of M1 means norm of first Zagreb index for the structures propane, isobutane and butane. So norm of M1 is equal to square root of sum of squares of sum of M1 values. So it means that square root of 6 square plus 12 square plus 10 square. And on simplification, norm of M1 is equal to 16.733. In the similar manner, M2 is equal to square root of 4 square plus 9 square plus of 8 square. So norm of M2 is equal to 12.688. Then forgotten topological index norm of F, that is equal to 36.385. Then we normalize the matrix. We normalize the matrix here by the definition Rij is equal to Xij upon square root of. So we use M1, norm of M1, norm of M2 and norm of F. So 6 upon norm of M1 value is equal to 0.358. Then 4 upon M2 12.688. Then 10 upon 36.385.275. So in the similar manner, we obtained second and third row values. Then apply equal weights. So already we discussed how to assign the weight values. So here we consider three indices called as M1, M2 and F. So we assign the weights in terms of equal weights. 1 upon 3 for M1, 1 upon 3 for M2, 1 upon 3 for F. So sum is equal to 1 only. Then we write the weighted normalized matrix. Weighted normalized matrix V is equal to first product of 0.358 with 1 upon 3, 0.119. Then 0.315 into 1 upon 3, 0.105. 0.275 into 1 upon 3, 0.098. In the similar manner, we obtained second and third row values. So these are called as weighted normalized matrix. Then we move on to next step, ideal best and ideal worst. So already we have the weighted normalized matrix V. So in the first column, the maximum of each column, maximum value of each column in the first column, maximum value is 0.239. Then in the second column, maximum value is 0.236. In the third column, maximum value is 0.275. So these are the ideal best values obtained from weighted normalized matrix. Next, ideal worst values. So take a minimum value of each column. So in the weighted normalized matrix, we minimum value is in the first column 0.119, in the second column 0.105, in the third column 0.092. So these are the ideal worst values. Based on this, next we need to find the Euclidean distances. Formula to find or compute Euclidean distances: square root of summation of Vij minus Aj plus whole square, and di minus is equal to square root of summation of Vij minus Aj minus whole square over the summation j varies from 1 to n. So here di plus Vij. So in the weighted normalized matrix, first row, first column, value, first intersected value 0.119. So Vij is equal to 0.119 and then minus Aj plus whole square. Aj plus means ideal best. Ideal best value A plus is equal to 0.239. So here in the similar manner, so we using 0.119 minus of 0.239 whole square plus 0.105 minus 0.236 whole square plus 0.092 minus 0.275 whole square. We get the D plus value for the structure propane. In the similar manner, isobutane 0.00, butane 0.120. These are from D plus. Then we move on to Di minus. So Di minus, here also we using the same procedure, ideal worst. So now square root of 0.119 minus 0.119 whole square. Then 0.105 minus 0.105 whole square, 0.092 minus 0.092 whole square. So values of D minus for the propane structure is equal to 0. So then in the similar manner, isobutane and butane. Then finally in the Topsys method, last step is closeness coefficient. Formula to compute closeness coefficient is Di minus upon Di plus plus Di minus. So we have Di minus for the C1. It means that for the first structure propane. So C1 is equal to Di minus value 0.0 upon Di plus value 0.255 plus Di minus 0. So and on simplification, 0 by anything value is equal to 0, propane C1 is equal to 0. Then we move on to C2. So C2 means isobutane. Isobutane, here Di minus value 0.255 upon Di plus value 0.00. Plus of Di minus is 0.255. So and on simplification, 0.255 upon 0.255 value is equal to 1. So it means that for the isobutane value is equal to 1. Then finally we move on to butane structure. So butane structure Di minus 0.151 upon Di plus 0.120 plus Di minus 0.151. So and on simplification, C3 is equal to 0.558. So for the butane structure. So here C1 for propane, C2 for isobutane, C3 for butane. Of these, maximum value is isobutane. C2 is equal to 1. Then C3 is equal to 0.558 and then C1 is equal to 0.000. So it means that isobutane more than butane, butane then propane. So first ranked candidate is called as isobutane. To allocate the ranks, here first rank molecule is isobutane. Next, we move on to second method called as Wiener method. So procedure or steps followed by the Wiener method is normalize the decision matrix. Here we use minimax method. So first Fij is equal to xj best minus xij upon xj best minus xj worst for beneficial criteria. Then xij minus xj best upon xj worst minus xj best for cost criteria. So in the chemical graph theory, we used MCDM techniques only in the beneficial criteria. So then compute utility and regret measures. Formula to compute utility and regret measures, SI is equal to summation of Wj into Fij, Ri is equal to maximum of Wj into Fij. Then we compute Wiener index. Wiener index is denoting by Qi is equal to V into Si minus S star upon S minus of S star plus 1 minus of V into Ri minus R star upon R minus R star, where S star comma R star, S star and R star best values of Si comma Ri, S minus R minus worst values of Si and Ri. V represent weight for strategy. So usually we use the weight of strategy V is equal to 0.5. Since probability sum is equal to 1, so it means that here we use the equal criteria. So V is equal to 0.5 implies 1 minus V is equal to 0.5. So final ranking. Rank alternatives by ascending QI. The one with the lowest QI is the best compromise. So now we consider same example already we discussed. So here X is represents the topological index values of M1, M2 and F. So column first is M1 means first Zagreb index values. Column second is called as second Zagreb index values. Column third is called as forgotten topological index values. So now here first best or worst per criterion. So in the first column best value, it means that maximum of 6, 12, 10. Maximum value is 12. And best of 6, 12, 10 is 12. Then second column best of 4, 9, 8, 9. And in the third column best of 10, 30, 18, 30. Then X worst, minimum of first column 6, 12, 10. Minimum is 6. Minimum of 4, 9, 8, 4. Minimum of 10, 30, 18, 10. So then difference of X best and X worst. So here 12 minus 6, 6, 9 minus 4, 5, 30 minus 10, 20. Then we normalize the matrix formula to normalize Fij is equal to Xj best minus Xij upon Xj best minus Xj worst. So normalized matrix F is equal to. So for the profane structure. So here in the formula Xj best. So X best 12 minus of Xij. Value of Xij. So 12 minus of 6 upon Xj best minus Xj worst 6. So 6 upon 6 value of M1 for the profane structure is equal to 1. Then we move on to second M2. So Xj best 9 minus of 4 5 5 upon 5 is equal to 1. Then 10 minus here 30 minus of 10 upon 20. 20 upon 20 is equal to 1. So it means that in the propane structure normalized matrix Fij values are equal to 1, 1, 1. In the similar manner isobutane. So isobutane here same 12 Xj best 12 minus of Xij is 12. 12 minus of 12 is 0, 0 by value 0 only. Then 9 minus 9, 0, 0 by 0. Then 30 minus 30, 0, 0 only. Next, we move on to butane structure. So here Xj best is 12, 12 minus of 10, 12 minus of 10 upon 12 minus of X means 10 upon 6. Right. Xj best is 12 minus of Xij is 10. So 12 minus 10 is 2. 2 upon difference value is 6. That is equal to 2 upon 6. Next Xj best is 9. 9 minus 8 is 1. 1 upon difference is 5. So 1 upon 5. In the similar manner 30 minus 18. 30 minus 18 is 12. 12 upon difference is 20. So normalized matrix values of butane structures 2 upon 6, 1 upon 5, 12 upon 20. Then we
Professor,
consider the
Doctor,
sir,
may I
tell me.
interrupt you here?
Please.
I don't want to stop you here, but unfortunately we don't have due to time restriction we have around 12 minutes, including question answer session. We have
Okay,
around
sir. Within 2 minutes I will
Uh,
complete, sir.
No. Your pace is going very good. As I wanted you deliver, you are delivering very good. But we have around 12 minutes. So no issue, you can continue like this, but keep in mind we have 12 minutes. So
Okay,
it's
okay, sir. Thank you. Right. Sir, here consider the weights criteria 1 upon 3, 1 upon 3, 1 upon 3. So equal weightage criteria. Then utility group satisfaction. SI is equal to summation of Wj into Fij. Then regret worst case dissatisfaction. Ri is equal to maximum of Wj into Fij. So values. So here we have the formula SI is equal to summation of Wj into Fij. So Wj means value of weight 1 upon 3 into Fij. Fij 1. So S1 is equal to. So here 1 upon 3 into 1 plus 1 upon 3 into 1 plus 1 upon 3 into 1 is equal to 3 upon 3. Value of S1 is equal to 1. Then second one 1 upon 3 into 0, 1 upon 3 into 0, 1 upon 3 into 0. Sum is equal to 0 by 3 is equal to 0 only. S2 is equal to 0. Then S3. S3 is equal to 0.333 into 1 upon 3 plus 0.2 into 1 upon 3 plus 0.6 into 1 upon 3. Value of S3 is equal to 0.3778. So these are the utility criteria, values of SI. Then we move on to regret criteria RI, maximum of Wj into Fij. So here maximum value of 1 is 1 only, 1 with 1 upon 3, that is equal to 1 upon 3 only. Value of R1 is equal to 1 upon 3. Then we move on to R2, maximum value of R2 is 0 only. So 0 into 1 upon 3 is equal to 0 only. Then R3. R3 here 0.333 with 1 upon 3, 0.111, 0.2 into 1 upon 3, 0.066, 0.6 into 0.2, 0.6 into 1 upon 3 is equal to 0.2. So maximum of 0.1, 0.06 and 0.2 is equal to 0.2 only. Then finally S star minimum of Si equal to 0 means here values of S1, S2, S3 minimum value of 1, 0.3 is equal to 0 only. Then R star minimum of Ri minimum value of R1, R2, R3 is equal to 0 only. Then S minus maximum of values of S, maximum of values of S1, S2, S3 is equal to 1, maximum values of R1, R2, R3 is equal to 0.333. Then finally we find the value of Qi, weak or index. Here V is equal to 0.5, V into Si minus S star upon S minus S star plus 1 minus of V into Ri minus R star upon R minus R star. So based on the above values, Q1 is equal to 1, Q2 is equal to 0, Q3 is equal to 0.4889. So here lower value indicates Q2 is equal to 0. So it means that in the weaker method, lower value indicates the more accurable. So isobutane less than next lower value 0.488, it means that butane, next value is propane. So first ranked molecule is called as isobutane in the weaker criteria. Then AHP method. So in the similar manner, we consider the AHP method. Okay. Sir? Hello? Okay. Sir, is it audible? Hello?
Yes,
Hello?
Professor, you are audible. Yes.
Okay, okay. Okay. Sir, in the similar manner, AHP method. So then finally we conclude chemical graph theory provides mathematical representation of molecules using topological indices. Then machine learning leveraged these indices to predict molecular properties accurately. MCDM techniques enable systematic ranking and selection of the most promising molecules. And then finally, integrating these three methods, chemical graph theory, machine learning, and MCDM techniques, approaches enhances efficiency, reliability, and decision making in molecular design, drug discovery, and material selection. Thank you, Professor. Thank you for all participants. Any questions?
Yes, please, the decorum of the forum is raise your hand if any participant has a question. Then we will call her name. Then he or she can ask question. In the meantime, I would like to appreciate my friend Dr. Shanmukha's talk on a hybrid mathematical framework, integration, chemical graph theory, machine learning, MCDM for predictive molecular property truly reflects the spirit of WAMA. He began from the foundational ideas and gradually built toward advanced cutting-edge application, perfectly aligning with our slogan, from understanding to advancement. His presentation beautifully demonstrated how deep mathematical concept can evolve into powerful interdisciplinary tools, guiding students and researchers from basic definition all the way to the impactful real-world application. Dr. Shanmukha, thank you very much for the beautiful and very understandable talk. So we have a question from audience. Usama, you may first you may ask question. Usama.
Thank you, sir. So I have a question that as we have studied in the chemical graphs that the chemical bonds in a graph are represented as edges. So why not in this examples of propane, isobutane, and butane, and there are hydrogen are neglected, and whereas it is making covalent bonds with carbon as well. Why is it neglected? As in the before, in the example, in the definition, here the Sir Shanmukha has mentioned that hydrogen is suppressed. Why it is suppressed? As from definition, it is also making bond, and hydrogen is an atom, and it is making a covalent bond, mutual sharing of electrons. Yeah, this was my concern.
Yes, sir. Thank you. So here, actually in the chemical graph theory, whenever we discuss topological indices, in the definition of topological indices only, we consider hydrogen suppressed molecular graphs. So only we neglect the hydrogen bonds, we consider the carbon bonds of propane or isobutane or butane only, sir.
As per my understanding, Usama, your question was that why we delete, neglect, or suppress the hydrogen atom. Usama, is it?
Yes, is it? Yeah, it is.
In the already we are discussed definition of Wiener index. In the Wiener index also we consider the hydrogen suppressed molecule only to find the Wiener index value. In the similar manner, we find M1, M2 and other topological indices. Any doubt?
Further adding to the answer, I guess from my point of view, consider only deleted or suppressed hydrogen atom to reduce our calculation. Because when we talk about isomers, we have two molecules like carbon and hydrogen. So whenever we have a carbon, if I go into a little chemistry, carbon needs four atoms to complete his outer shell, electrons to complete his outer shell. So if we have C1 as if carbon has a carbon bond, it's mean three hydrogen atom are needed. Similarly, if a carbon has a bond with two carbon atoms, it's mean two hydrogen needed. So it is very understandable for chemist. So they allow us that we can neglect the hydrogen atom to reduce the calculation, to reduce computation of or from calculation point of view. It's my observation.
Yes, sir. Yes, sir. Thank you.
Okay, Doctor, we have another question from Miss Sahrish. Sahrish, you can
Okay.
ask the question now.
Please.
Thank you, sir. I have a question. When we learn the method MCDM,
Yeah.
in all examples, we use the weight 1/3. So what's the reason we are using 1/3? Is it the reason because we are discussing the three molecules or anything else?
No, madam. Suppose you consider 20 molecules, 25 molecules, any number of molecules. So in this case, usually we use the weighting criteria is equal to sum is equal to 1 only. Basic probability theory. So only here we consider 1/3, 1/3, 1/3 equal weight.
Okay, thank you so much. It's clear now.
Sahrish, sorry,
Yes, sir.
as per my understanding, I guess the question was that why we consider equal weights? The reason is that we consider three indices.
Yeah, here
Yes,
we can.
sir. The three
Is that the
indices.
is that the reason? I guess this is not the reason, I guess.
Sir, suppose we use
Yes.
0.25, we assign values 0.25 for first index, 0.5 for second index, 0.25 for third index. So weightage is equal to 1
Very
only,
good.
sir.
Yes.
Ah.
Yes. So may I ask, because I write this question on my paper, that why we consider 1/3 equal? Is there some specific reason? I mean, as you said that if we consider 0.25 plus 0.5 plus 0.25, the sum is 1. So if we change the weight, like I want to give more weightage to the first Zagreb index and less weightage to the forgotten index, then what will be the difference or what will be the behavior or what will be the result?
Actually, I don't check, sir. I will try, sir.
I
Okay,
think
no
when we are applying the weight,
issue,
sir,
no
is it not compulsory we
issue.
have to
We
give
can
the equal
discuss this
weight?
later. But some more, yes.
Please.
There must be some reason. If at least if you give equal weights, there must be some reason. But I guess this is not the reason that we have to give the equal weights. Because I worked on little on MCDM, so it depends upon us. I mean, if I want to give more weightage to some index, so it is my liberty. It is my hand that I give him more weightage or to the important index.
Yes, sir. Yes.
So let's try to find the reason. Anyway, another question I have, Doctor, from my side, that
Okay.
usually when we talk about my friend about involving machine learning,
Okay.
into predictive properties, they usually say that considering only 20 entries, 20 molecules to train our data, train our model is not enough.
Yeah, yes, sir. Yes, sir. Obviously. Uh, we
They
consider
are
only one example.
because
To
I
take one
tried it.
example. More number of
Okay,
data.
okay. So we need. They said that yes,
We consider more number of
because they
data.
said that exactly as much data as we have, we get better results.
Better results. Yes, sir.
Okay, thank you very much, Dr. Shanmukha. Thank you again. Unfortunately, up to now, I cannot collaborate with you on this topic, although I have a research group here with my under my supervision who are working on the same topic. But soon we will get in touch with you to have some collaborative work.
Thank you, sir. I thank the university for the opportunity. Thank you very much.
Okay, thank you
Thank you for
from our side. Thank you, doctor. From now, you can sign off. Thank you again because our next speaker is here with us, and we will go to the third talk of